Good day. We will continue with the ulangan paper of STPM 2021, Section B. Two air-filled parapet capacitors C1 and C2 of capacitance 10 and 20 microfarad respectively are connected to a battery of 24 volt and a switch as shown in the circuit diagram. An insulator of dielectric constant 5 is then inserted into the space between the plates of C1. When switch S is closed, calculate the total impedance of the circuit. So we learned about the effect of the dielectric constant, and we also learned about the formula of the capacitance. So when you have dielectric inserted into the A field capacitor, what we have is the epsilon R multiply the epsilon naught as the new permittivity of the medium. So before we calculate the total capacitance, let us calculate the new capacitance of C1 with the dielectric. So what we do is 5 multiply the original capacitance of the air field capacitor C1, which is 10, and you obtain 50 microfarad. So this is how you get the new capacitance for the dielectric. And for the total capacitance, they are connected in parallel. So simple, we just do addition, 50 plus 20, and you will obtain 70 microfarad. We move on to question B. Determine the total charge stored in the capacitors. We have the new capacitance and we have the voltage. So just apply the formula of Q equal to CV. We have the 70 microfarad, multiply the voltage, 24 volts. And you will obtain 1.68 millicoulombs. Okay, 1.68 times 10 to the power negative 3 coulombs. Move on to question C. S is then open and an uncharged capacitor of capacitance 5 microfarad is then connected in parallel to C2. Calculate the potential difference across the capacitors. So this issue has been discussed in my video about the capacitors in series and parallel. So what will happen is that they will perform charge redistributions. So the battery is disconnected, so the total charge in the circuit is conserved. So before we talk further about it, so let us imagine what is happening at the final end or the steady state of these three capacitors is that they are in parallel. So the final voltage across each of these components should be equal. So first, we need to obtain the new effective capacitance that we have 70 plus the 5 microfarad since they are in parallel equal to 75 microfarad. And if you have watched my video, what we're going to do is we utilize the condition of the final state of the capacitor that the voltage is equal. Okay, so the voltage is the ratio of the total charge to the total capacitance. So the total charge has been obtained, which is 1.68 milli divided by the new effective capacitance, 75 micro. And it is equal to 22.4 watts. And since three of these capacitors are in parallel, so three of them having the same potential difference, which is equal to 22.4 volts as the final answer for this question. So you can watch back the video if you're still not sure how to do it, and we'll proceed to the next question. Question 17, resistor R, inductor L connected in series to an AC voltage supply. So this is RL circuit. We have voltage of peak as 25 volts and a frequency of 50 hertz. Resistance is 50 ohm and the reactance of the inductor is 30 ohm. So you learn about the formula of the reactance of the inductor. Question A, you need to determine the self-inductance. So remember the formula is XL, okay, the reactance equal to 2 pi FL. So to obtain the self-inductance, so what we do is we get the reactance 30 ohm divided by 2 pi F, okay, divided by the frequency which is 50 hertz. And you will get the inductance as 0.095 Henry. Okay, simple. We move on. Calculate the impedance. You have the resistance. You have the you have the reactance also. So just apply the formula that the impedance is equal to the square root of R square. You have 15 square plus the square of the reactance, 30 square. And in the end, you obtain the impedance as 33.54 ohm. Okay, so next, determine the root mean square of the current. So to calculate the root mean square of current, you need to use root mean square of the voltage, and we have the formula of V equal to IZ. Okay, so we have the voltage as 25 volts, which is the peak voltage. So we need to convert to root mean square by divide the value by the SERT2. So we have the 25 over SERT2. So that is the root mean square voltage. And to obtain the current, we need to use the voltage divided by the impedance. So impedance is equal to 33.54 ohm. So 25 ohm divided by SERT2 is the root mean square of the voltage, and then divide by the impedance. And you obtain the current as 0.53 ampere. So that's all for section B. We move on to section C. Question 18, state Kirchhoff law. So this is definition, and you should have learned it in your textbook, so I will skip it. We move on to B. A potential divider which consists of 100 centimeter length wire with resistance of 2 ohm is used to supply variable voltage to a table length of resistance 3 ohm as shown in the circuit diagram. So the voltage supply has an EMF of 3.3 watt with negligible internal resistance. Determine the range of voltage supply to the table length. So you have learned how the potential divider can be used to supply variable voltage, that we just move the jockey or the known as a slider, okay, at point B between point A and C. So the range means that you need to obtain the minimum and the maximum value for the range. So the minimum is the point B is connected to point A, that the voltage is equal to 0 watt. And for maximum voltage, it can be connected to point C to obtain the full potential difference across A and C. So since we ignore the internal resistance, so the maximum is equal to the EMF of the battery, 3.3 watts. So if you have the internal resistance, so you will expect a lower maximum voltage because we have a voltage drop across the internal resistance. So the range is from 0 to 3.3 watt for the first question. Move on to question 2. If the length of the wire from A to B is 60 centimeter, so this means that from B to C is 40 centimeter. Determine the currents I, I1, and I2. So this is something, a straightforward circuit that we learn. Okay, something you have done it before in SPM level. So for my advice, let me convert the circuit into the diagram as shown here. Okay, so the wire is converted into two resistors, R1 and R2, that R1 represent the 60 centimeter long of the wire, while R2 represent the 40 centimeter long wire. And we learned that the relationship of the wire with the resistance, that the length is proportional to the resistance. So we know it is 100 centimeter with the total resistance of 2 ohm. So R1 is 60 centimeter, that we have 60 over the total length, which is 100 centimeter, multiply the total resistance 2 ohm, and you obtain 1.2 ohm as the R1. For R2, it will be the remaining resistance, which is 2 minus 1.2, and it is equal to 0.8 ohm. So this is how we can convert the previous circuit into this circuit, and you can solve it like how you do it in the SPM level. So some people might suggest to use Kirchhoff law, but in my opinion, it is too advanced for this simple circuit. Okay, you still can proceed with Kirchhoff law, but let me show you a simple way to do this question. So first of all, how we do in SPM is we need to obtain so before that, we need to obtain the current. So to obtain the current, maybe we need to obtain the voltage first. So before we obtain the voltage, we need to obtain the equivalent resistance. So this is how we can do the logical thinking to solve this question. So first of all, let us get the equivalent resistance between R1 in parallel with 3 ohm. So R1, which is 1.2 ohm in parallel with 3 ohm. Okay, so that is equal to, okay, ignore this one. So 1.5, it's 1.2. So 1.2 times 3, 3.6, divided by 4.2. And you obtain 6 over 7 ohm. Okay, so that is the resistance of the R1 in parallel with 3. And then we want to obtain the voltage across the R1 or the 3 ohm. Then we can apply the formula of potential divider. So the voltage across the table lamp that we can label as R1 or 3 ohm. Okay, it is equal to the resistance, which is 6/7. Okay, divide by the total resistance 6/7 plus, so the resistance of R2 is 0.8. Okay, multiply the total voltage 3.3 watts. So what we have is 6/7. Okay, divide by the 6/7 plus 0.8. And then multiply 3.3 watt and you will obtain 1.71 watt. So that is the voltage across the table lamp and also the voltage across the R1. And then now we want to obtain I1, I2, and I3. So, sorry, this is I1, okay, this is I2. Okay, so now we just obtain it slowly. So I1 is equal to the voltage 1.71 divided by R1, okay, which is 1.2 ohm. Okay, so this one divided by 1.2 ohm and you will obtain 1.42 ampere. So that is I1. And then we can obtain I2. So we just use also the same voltage, 1.71 divided by 3 ohm. And you obtain 0.57 ampere. And then to obtain the current, so based on the Kirchhoff current law, okay, so you can mention based on, okay, so here we can use the KCL because it's simple, okay, KCL, so I is equal to the total current, okay, because I is the entering and I1 and I2 are the one who flowing out from the point. So it's the formula is I is equal to I1 plus I2, so 1.42 plus 0.57 and you will obtain 1.99 ampere. So that should be the final answer for this question. So for those who apply Kirchhoff law, maybe you can let me know if you can get the same answer. So we proceed to the next one, determine the power supply to the table lamp. So simple, we can just apply the formula P is equal to I square R, or you can use V square over R, okay, it's okay. Or maybe you can also use V power equal to VI because we have all the information. So for here, maybe let me use the current, where the current through I2 is 0.57. So if you're not sure, you can just use the V square over R for safety purpose. So for 0.57 square, multiply the resistance 3 ohm, and you obtain 0.971. Okay, so you also can do checking that V square over R, 1.71 square divided by the resistance, and you also obtain the same answer. Okay, so next, explain the change in power supply to the table lamp when the slide wire contact is moved towards C. So we are going back to the circuit. So if we move towards C, what happens is that the voltage supply to the table lamp is increasing. So like I said, the voltage range from 0 to 3.3 when we adjust the point B between A and C. So when it is moving toward point C, what we can see is that the voltage supply to the table lamp is increasing. So based on the formula of power equal to V square over R, okay, we don't care about the current because we need to recalculate again. So for here, it is very straightforward that we just mentioned about the voltage. So when it is moving towards C, so when the slide wire contact move towards C, so the voltage is increasing. Okay, voltage supply to the table lamp is increasing. So the power and hence the power supply is also increasing. So this is a simple and straightforward explanation to this question, 2 marks. Okay, so we move on to the next question, 19. Uniform magnetic field B is applied perpendicularly to the direction of current in a semiconductor of width W shown in the diagram. So you need to recall back what we have learned about the Hall voltage. Number one, explain Hall effect of the semiconductor, 2 marks. So maybe you need to at least explain 2 effects from the Hall voltage. So simple, magnetic force that acts on the moving charge causes the left side and the right side surface of the semiconductor. So you need to be sure because the current is flowing in this way. Okay, so example, we have a charge here. So the magnetic field will push the charge either to the left or to the right. Okay, so if you apply the Fleming left-hand rule, you will know the direction. Okay, to be positive and negatively charged, so this provides the electrostatic force that counter the magnetic force, which enable the electron to move in a horizontal line. So you can explain it, okay, as what you have learned in the textbook. So this is just a sample answer provided by me. So second question, derive an expression of Hall voltage across the semiconductor. So this derivation can be obtained from the textbook. So let us do the revisions. So we start with the formula of Fe equal to Fp. So this is what I mentioned in the first question. So we have the electrostatic force QE equal to the magnetic force on the moving charge, with QVB. So the electric field strength is equal to the, so we expect the voltage is here. Okay, the voltage either positive or negative. So it is the potential difference divided by the W. Okay, so this is the electric field strength in this case. So the potential difference divided by W equal to VB. Okay, and then what we have is the Hall voltage V is equal to W VB. So is this the end? No. Okay, we can still continue that. We can apply another formula, which is I is equal to NEF. Okay, I is equal to NEF. So from here, we have the drift velocity is equal to I divided by NAE that you can put into the formula. So substitute in, you will obtain the Hall voltage as WB multiply I over NVE. Okay, so there's something missing in this question, that they didn't label the thickness and the length. Okay, so maybe you can label yourself that the thickness should be here. Okay, this is the thickness, and this should be the length. Okay, this is the conventional labeling. Okay, so for here, what we have is the W. Okay, sorry, this is NAE. Okay, so what we have is the area and the width. So what we have in the end is the Hall voltage is equal to IB over NET, as what we have learned before. Okay, so because area is equal to the W multiply T. Okay, this is how we obtain the area of the surface. Okay, so in the end, this is the formula of the Hall voltage. Okay, and then number 3, stat 3 applications. So this is you can refer to the formula and stat the function. Okay, so first of all, we can obtain the type of charge carrier. Okay, this is what we have mentioned in the video or in the textbook. Second, okay, based on the formula, we can measure the magnetic flux density. Okay, and one of the instrument mentioned is the Hall probe. And of course, you can measure the current, and also you can measure the charge density. So these are the application of Hall voltage that you can write in the answer. And please don't use the thickness, okay, because thickness can be measured by using a ruler. Okay, so don't use thickness, okay, because unless you don't really know the answer, but these are the 4 answers that you can provide for this question. We continue with the next question. A thin slab N-type semiconductor of length with thickness carries a current of 130 milliampere. We have the magnetic flux density of 0.5 Tesla, produces a maximum Hall voltage of 9.15 milliwatt. Calculate the number of free electron per unit volume within the slab. So you should know the number of free electron per unit volume is the electron density, and you have the formula of Hall voltage, okay, that you derive in the first question. Okay, so we have the voltage 9.15 milliwatt. Okay, we have the current, we have the magnetic flux density, and we also have the thickness. So everything is there, so you can just put into the formula and obtain the value of the electron density. So what we have is 0.13 times 0.5 divided by the charge of free electron divided by thickness 2.5 milli, and then divide by the Hall voltage 9.15 milliwatt. And that is equal to 1.77 times 10 to the power of 22 electron per meter cube. Okay, so this is the unit of electron density. Okay, then we move on to the next one. Determine the magnetic force that acted on each electron. Okay, each electron. Okay, so we have the formula FB equal to QVB equal to QE. Okay, we don't have drift velocity, so maybe we can use the formula of electrostatic force because they are equal, okay, as what I mentioned in the derivations. So you don't use the QVB, but we can just use the QE, and the E is equal to V over W. So the only things that we don't have is about the charge, okay, but we just need to obtain the magnetic force that acted on each electron. So from the chapter 14, you learn about the charge is equal to the number of electron multiply the charge of an electron. So from here, the number of electron n, so we can just put into the formula of Fb. Okay, and then E is equal to n, number of electron multiply the charge, and then V over W. So to obtain the magnetic force per electron, so it is expressed as Fb per n. So this is the one unit. So equal to E V over W. Okay, so the charge of an electron multiply the whole voltage 9.15 milliwatt divide by the width. Okay, the width is equal to 7.5 milli. So this is how you obtain the answer for this question that is equal to 1.95 times 10 to the power of negative 19 Newton per electron. Okay, so maybe you can mention about the unit. Okay, so this is how we solve this question. We move on to the last question, question 20. Pure inductor L, a resistor R, and a switch S and an emitter are connected in a battery of negligible internal resistance as shown in the circuit diagram. Self-inductance, resistance, and the EMF are given here. So when the S is closed, the increment of the emitter reading is slow. Explain the reasons to the slowness. So you learn about what happened to the inductor, okay, for a pure inductor circuit, that there is a back EMF. So this is the reason that caused the slowness. And this is related to the topic of the self-inductance. So this is the sample explanation for this question. So initially, there is no current flow in the circuit. So you need to recall back what is about the self-inductance. Okay, when the S is closed, current start to flow, which means there's an increase in the current. So there's an increase in the magnetic field linked to the inductor. And based on the Faraday's law and also the Lenz's law, so there's an induced back EMF in the inductor that opposes the current in the circuit. And this is the reason that it slows down the increment of the current. So this is actually related to the self-inductance of the inductor. Move on to the next one. Determine the final current in the circuit. So this is also about the self-inductance that in the end, there is no opposition by the inductor, okay, for the final steady state of the circuit, that we can actually just short the inductor. And to obtain the current, we just use the V equal to IR. So we have the voltage as 6 volt. So the current is equal to 6 volt divided by the resistance 1.6 ohm. So simple. So 6 divided by 1.6. So the current is equal to 3.75 ampere. Next, calculate the rate of change of current when the current reaches 2 ampere. So this is a little bit difficult, okay, so but you just need to remember about the things you have. Okay, for example, we can apply the control flow, and we know that the EMF should be equal to the voltage across the inductor plus the voltage across the resistance. Okay, we have the current, and we also need to obtain the rate of change of current. So where did we see the rate of change of current? So from here, we can actually further derive this expression that the EMF E is equal to the voltage across inductor as equal to the L di dt. Okay, so this is the one we learned. So, and then this is the di dt that we need. And then the voltage across the resistance is equal to IR. Okay, so from this expression, we can see that we almost have everything. We have the EMF is equal to 6 watt. Okay, we have the inductance as 4 Henry. So multiply di dt. X6 equal to 4 di dt. And then we have the current. So given current as 2 ampere plus times the resistance 1.6 ohm. So everything is there. So this is how you need to remember your fundamental. So from here, we can calculate the rate of change of current. So it is equal to 6 minus 2 times is 6 minus 2 times 1.6, and then divide by 4. Okay, so you would have 0.7 ampere. Ampere per second. So this is the unit of the rate of change of current. So we move on to the next question. A circular loop wire which is connected to a resistor R placed in a uniform magnetic field B directed into the plane of the pitch. So this is something confusing, okay, for me. So the area is given, magnitude of the magnetic field is 1.35 Tesla, and the resistance R is 1 ohm. The loop is moved up and down along the y-axis for the 0.05 second. So for this question, I feel there's a little bug on the language. Okay, we do not understand what is meant by the loop is moved up and down. Okay, so let's try and answer the first question first. R becomes hot after the loop is moved. Explain your answer. So this is due to the Faraday's law that there is a change in magnetic flux, that there is a induced current in the circuit. So how do we explain? When the loop is moving out from the magnetic field region, okay, we need to be clear with this. Should be moving out. Okay, it's only moving around the magnetic field. It doesn't induce the current. Okay, it should have the change in the area. So when we say the loop is moving out, so there will be change in magnetic flux linkage. So based on Faraday's law, this will induce a current flow in the loop, which will flow through the resistor R. So there will be a power dissipation across R as heat energy that causes it to become hot. So from the explanation, there's something that is very important, is that the loop must be moving out or moving into the magnetic field region. Or another way to induce the current is by rotating the coil, but it is only moving up and down. So this is why I'm a little bit confused with this question, but it's okay. So let's assume that the loop is moving out from the magnetic field, okay, something like this. Okay, moving up. Okay, and then moving down. Okay, so this is the assumption that I will be made to solve this question. So let's see the question 2. Determine the current in the circuit. So this is the challenging part. So we have E is equal to dV dt, and the flux is equal to B times E. So we have the resistance is 1 ohm. So we need to get the current, so 1 ohm can be ignored. So I is equal to the magnetic flux density, 1.35 Tesla, multiply the rate of change of the area. So here I will assume that moving out and into the magnetic flux density as 0.05 second. So for here, let us assume that the time to moving out is 0.025, which is half of the time, and then moving in again for 0.025 second. So this is the only assumption that I can be made. But if you have other opinions to solve this question, then we can leave it in the comment section and let me know, so we can have further discussion about it. So for me, let me assume that it's moving out and in along the y-axis for 0.05 seconds. So the time here is only half of it. So the area given is equal to 33.5, okay, 33.5 centimeters square, which is equal to times 10 to the power of negative 4, and then divide by the time. So here I will assume is moving out and in is equal to 0.25 seconds for moving in, okay? So this is what we can do, okay? So 1.35 multiply the change in area that is moving fully out from the magnetic field, 33.5, divided by the time. So the current is equal to 0.18 ampere. Okay, so current is equal to 0.18 ampere. So this is a sample solution for me. If you found any mistake in the paper, you can let me know. It doesn't mean that the paper is the solution in this video is 100% correct. Okay, so if you still have any question, you also can leave it in the comment section below. So that's all for the discussion. Thank you for watching.